Why was it that ether and chloroform were the anesthetics that were discovered? They were available, of course, and that of course, is one answer, but what characteristics of those anesthetics made it really feasible for them to be used to deliver anesthesia at that time? What was it?
They were very potent, for number one.
They were potent. That was vital. Why was potency vital?
Just because you didn't really have a closed system in which you could contain it. So you had to either, I mean, pretty much you either put it on the cloth and put it over their face, so you wanted something that once they inhaled it, because you were going to lose some to the atmosphere.
Right. So you really had to be able to deliver a lot in order to get anesthesia to occur. Not only because you had this dilution, but because they were very soluble agents. Okay, any other reason, though? That they had to be potent. Why wouldn't nitrous oxide do? It was suggested, at the time. But why wouldn't nitrous oxide do?
Just because since they didn't have very good control over the delivery of the anesthetic, they had to make sure that they were able to maintain a good enough concentration that the patient did not move during surgical stimulus.
So concentration was vital, but what else was vital that you deliver to the patient?
Oxygen. But
Oxygen. What do you mean oxygen but? Oxygen, yeah, we had to deliver oxygen. And if they weren't potent, you would dilute the oxygen.
okay.
So they had to be potent for the reasons that you suggested, and because we had to deliver enough oxygen. So we got anesthetics such as diethyl ether. Here are these wonderful old bottles of ether. I shouldn't say so old. This was the can that it came in that I used to drip ether from. Well, yeah. It allowed anesthesia to be delivered. They had to be allowed to be delivered in a very crude way. There weren't any delivery systems. I mean, there weren't any anesthetic machines before there was anesthesia. So you had to be able to deliver it in a crude system with a mask, for example, like this Yankauer mask, where you see the mask itself, and that was covered with gauze. And you had, as you say, air coming in and the vapor coming in, either chloroform or ether. And the carbon dioxide you got rid of all by dilution with room air. So you had this great lack of control. And we have, with enormous effort, gotten a bit of footage of the first ether anesthetic. Doesn't look very glamorous, does it? This is being done by a real master of the open drop ether method, Dr. Bill Wren, Irish anesthetist. And it looks like it's a very old film, but in fact, it's a reasonably modern one that Dirk has managed to make look very old. Now, the limitations of this approach have already been articulated. We really had no control over the anesthetic concentration. And because of the high solubility of the agents that we used, ether and chloroform, the recovery was often prolonged after anesthesia. There were incremental improvements in the anesthetics and anesthetic techniques that followed the discovery of anesthesia, but most of these were really pretty trivial. The delivery of anesthetics in a controlled fashion awaited the development of what vaporizer? Anybody know? What was the vaporizer? Yeah. What
Was it the copper kettle?
The copper kettle, that was it. The copper kettle, this magic device that was produced by Lucien Morris. And there it is, the copper kettle, sitting on a copper top. Why was it copper?
Conducts heat well.
It conducts heat well. That was it. That was the whole answer. And you put it on a copper tabletop so that, again, you could conduct heat. Why did you want to conduct heat well?
When the anesthetic vaporizes, it draws heat out of the room or out of the container, so the container will cool.
Right.
So the container needs to be able to draw heat back out of the room.
Right. So in order to keep the temperature constant in there, and therefore keep the vapor pressure constant, you wanted to keep the vaporizer in contact with room air, so it just wouldn't decrease its temperature. The basis for the copper kettle was this. You had a flow meter that was devoted to nothing but flow through the copper kettle. And the outflow of that, bubbling through the anesthetic, was added to the flow from a second flow meter. And if you knew both those flows, you could calculate the concentration of ether or isoflurane or whatever you put in there. For example, let's suppose you had 100 mil per minute going through the vaporizers. You got 100 mil per minute. And you add to that some vapor. And you could now calculate how much vapor you'd have to add. You had to know one thing, though. You had to know what the vapor pressure was. So let's suppose the vapor pressure was that of ether, perhaps a half an atmosphere at ambient temperature. So you'd have 100 plus a certain amount of ether to give a concentration of what? Well, let's think about it. What was X? If the vapor pressure is half an atmosphere, what does X become if the flow through here is 100 mil per minute? What does X have to be in order to make the resulting concentration 50%? No, I want it in milliliters. I want it in milliliters. What does X equal in milliliters? You're going to have to make this so that X over 100 plus X equals 0.5.
100.
100. Give that man a cookie. That's right. Okay, but now let's suppose the vapor pressure were different. Let's suppose the vapor pressure were a third of an atmosphere, so that this had to equal 0.3. Now what does X become? 0.33, I should say. 0.333333.
50.
50 is right. 50 is right. So you can calculate that. You guys are really good. You guys are really good. The reason this ceased to be the delivery system was because the calculations were so hard. They really weren't that hard, were they? But in fact, that's right. That's why this ceased to be. So if you knew you got 100 cc's and you added that to, say, 5 liters, you had a concentration of 2%. So you could calculate it all out. Or if it were 50 cc's and you had 5,000 cc's going by, it was 1%. In fact, people used to put the diluent flow at 5 liters when they were giving isoflurane because it made it easy to calculate the concentration of isoflurane that they thought they were delivering. Each 100 cc's was 1% more. 1% more. But we didn't like that. Anesthesiologists, anesthetists of all sorts, are loath to do mathematical calculations. And so we developed the TEC-type vaporizer. And there's a schematic of the TEC-type vaporizer, also called the variable bypass vaporizer. Why is it called a variable bypass vaporizer? We got an answer already.
It has a bypass cone built into the system so that you have flow not only through the canister but also through the material that you're using as the anesthesia.
And you vary that bypass,
Correct.
and therefore variable bypass. So gas comes in to the vaporizer and can go to one of two places. It can go down here where the liquid anesthetic is, the sump, and pick up anesthetic, come back up here, and join with the flow that has bypassed the vaporizer, bypassed the sump. And there's another little device here called the temperature compensating valve that compensates for changes in ambient temperature and keeps the output constant despite changes in ambient temperature and therefore changes in the vapor pressure of the anesthetic. So these two flows are then combined and put out to our anesthetic circuit, which we're going to talk about in just a minute. Simple device, and entirely swept away the copper kettle because now all you had to do was turn a dial and look at where the dial was set at. It didn't matter what flow you had, didn't matter what the ambient temperature was. In the copper kettle, you had to know what the temperature was. If the temperature was cold, you had to make a correction for that. If it was hot, you had to make a correction for that. Wow. That's what you wanted. That's what you wanted, even though it cost a few $1,000s. But then we got desfrane. And we have a problem here. Because you put desfrane in this vaporizer, and the room is heated up to deal with the baby, what happens to the desfrane? It all boils away. There's no controlling it. You don't have to put any flow through here. The desfrane will just come out. It'll come out at an infinite concentration, well, at 100% concentration. So a new vaporizer was devised. The Tech 6 vaporizer. And functionally, that is in terms of what you see as an anesthetist, functionally, it isn't any different from the variable bypass vaporizer. Doesn't matter what flow you've got. Doesn't matter what temperature the room's at. You get the output that you put on the dial, the vaporizer dial. And here's how it works. You have flow meters. I've just drawn one here, but it also could be an oxygen plus a nitrous oxide flow meter or oxygen plus air or whatever you like, going into the vaporizer. At the same time, you've got anesthetic in a sump. The anesthetic is desfrane, and it's heated to make it a gas. So we have desfrane now heated at about 1,500 millimeters of mercury, about 2 atmospheres pressure. And that's available to add to this gas stream. But before it can be added to that gas stream, it has to pass by 2 resistances, one of which is controlled by a differential pressure transducer, and the other is controlled by you. There's a third resistance here, a resistance that the bypassing gas has to get through. The fact that there's a resistance here means that there's some pressure here. There's also some pressure over here. And this differential pressure transducer senses the difference between the two and equalizes them by adjusting this resistance. So if the flow here goes up, it will increase this pressure by reducing the resistance here and allowing more desfrane to enter this arm of the circuit. Flow goes up, more desfrane. Flow goes up, more desfrane. Flow goes down, pressure here goes down, less desfrane. If we open this valve, what will that do to the pressure here? It'll drop it. And so what will the differential pressure transducer say?
Less desfrane.
It will say there's less desfrane than what there was, and I'm going to make that equal again. So it will open this up. So when you open that further, you get more desfrane. An ingenious device. There were several possible solutions, but this was a very clever one. But an even more clever one is the more recent ADU vaporizer. ADU stands for Anesthetic Delivery Unit. At one time, I thought it wasn't going to be possible to make a variable bypass vaporizer that would accommodate desfrane. Not true. I was wrong. The ADU vaporizer does accommodate desfrane. And it does it in a clever way. The way it does it is to control not what gas goes into the vaporizer, but how much comes out. It controls the flows through the vaporizer, both the bypass flow and the flow coming from the anesthetic sump. And by knowing what pressure is in the anesthetic sump, and by knowing the temperature of the sump, temperature of the liquid anesthetic, it can calculate the concentration that should exist in this flow coming from the vaporizer. And it can adjust the relationship between that flow and the bypass flow to give the concentration that's indicated on the dial. So this is all done with a computer within the vaporizer, with both hardware and software. It allows one other nice feature, which is that the vaporizer is specific for the anesthetic, but the vaporizer itself, what's called the Aladdin cassette, can be specific to different vaporizers in the hardware and software can deal with all of them. That is, one vaporizer, in effect, can deal with all the anesthetics that we might want to use, the sevoflurane, the isoflurane, or the desflurane. A clever device. So we've got 3 general vaporizer systems. There's a 4th that isn't quite on the market yet, so we aren't going to discuss it. And let's go on now to some real and some imaginary concerns about the delivery of anesthesia with these vaporizers, particularly the ones that are powered by electricity. There is one concern regarding desflurane. If we give 10% desflurane, that's going to decrease the concentration of oxygen in the gases that we deliver. And one of the concerns has been, well, if we give 10% desflurane, won't that decrease the concentration of oxygen by 10%? If we're giving 30% oxygen, won't that produce 20% oxygen? And aren't we getting dangerously close to a hypoxic mixture? Do I see anybody going like this? No? All right, let me see. How many are going like this? All right, now you, sir, tell me why you're going like that.
Well, because if you decrease, if you have 30% oxygen, you'll have 70% of another gas.
Right.
And you're going to take 10% total reduction of that. So you'll decrease oxygen from 30 to 27%.
And not 30 to 20%. And we did that, didn't we?
James, I see that you're using 70% nitrous today. You have your fresh gas flow at 7 liters and your oxygen at 3 liters. What are your plans for volatile anesthesia?
We're going to use desflurane, and we're going to increase our volatile agent to 10%, and then we're going to look at the reduction in oxygenation and in nitrous oxide content.
And I see that right now we have 30% oxygen and 70% nitrous with just a trace amount of desflurane. So let's see what happens to the concentration of oxygen and nitrous oxide as we turn the dial here to 10%. What seems to be some of the confusion behind turning this to 10%? What do you think it will do to the oxygen and nitrous?
Well, a common mistake may be that one would think that by adding 10% desflurane, we'll reduce our oxygen concentration to 20%, which would be a hypoxic mixture. But in essence, what we're going to do is decrease our oxygenation by 10%, which would bring our O2 to 27%, and will decrease our nitrous oxide content by 10%, which would bring us down to 63% nitrous.
Well, lo and behold, we already see nitrous oxide decreasing from 70 to 62, and our oxygen, starting at 30%, has been now hovering around 28. And you're predicting a 27% oxygen?
Yes.
But we're not quite up to 10% desflurane.
Right.
So I suspect as soon as we get up to 10% desflurane, we'll see those changes. And sure enough, we're approaching now exactly 63% nitrous, and I saw a quick 27% oxygen. There it is.
27%.
As we approach 10%. Well, very good. I think that clears up the confusion for me.
The romance of physics. That was an imagined concern. There's some real concerns. One is the fact that the ADU and the Tech 6 vaporizers are powered by electricity, so you have the potential for failure. If you have failure of the electrical source, they've each got batteries in them. Will that do to sustain their output? Yes or no? How many say yes? How many say no? No, the no's have it, and that's right. The little battery is only intended to perform a few functions, neither of which is to allow the output to continue. There is a concern that is a very subtle one that relates to altitude. Not all of us have the good fortune of living at sea level. Some people live in Denver, some people live in Leadville, Colorado, and the output of vaporizers is going to be influenced by altitude. Let's suppose, for example, we were attempting to give anesthesia at the top of Mount Everest, and we were going to use a variable bypass vaporizer. Now, the top of Mount Everest is about 1/3 of an atmosphere. What would be the output of the vaporizer for isoflurane at the top of Mount Everest? Yeah, do you know?
About
Do you
100.
know?
It seemed like it'd be about 100%.
It would be 100%. That's right. Now that'd be for the variable bypass vaporizer. And let me just remind you of that here. And that's the correct answer, because a third of an atmosphere is what the vapor pressure is. Of course, we didn't take into account the fact that it was 0 degrees or maybe minus 50 degrees at the top of Mount Everest. But assuming it was still 20 degrees centigrade, indeed, this would now boil, and you'd have 100% isoflurane at a third of an atmosphere. But it still would be lethal. Still would be lethal. So increasing altitude increases the output, the effective output of the variable bypass vaporizer. What about the ADU and the Tech 6 vaporizers?
No.
Will the output, will the concentration remain what it says it is? Will the concentration remain?
The concentration stays the same, but you're multiplying by a smaller atmosphere number. Instead of 760 torr, it's 500 torr. So 1% of 760 is 76, but 1% of 500 is
Going to be
is-
2/3 of that.
right.
Very good. And that's the answer. That's right. So when you go to altitude, you got to keep that in mind when you're using these vaporizers. Now let's go on. We've talked about the anesthetic machine. That is the device that concocts the anesthetic, that produces in the delivery hose the anesthetic concentration that you decide you want. That delivers it to what we call an anesthetic circuit. Why do we call them circuits? Why do we call them circuits? Anybody, come on. Circle, 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 circle. What circles?
The circuit is actually in a circle configuration.
To enable what?
Replenishment of the gas, and with the unidirectional valves, you don't have rebreathing.
You don't have rebreathing, that's correct. But why do you put it in a circle?
So you don't have to use as much anesthetic.
So you do have rebreathing. You don't have any rebreathing of what?
Carbon dioxide, because we
Right.
have an absorber.
Because it's been absorbed, because you have recirculated it. You've circled it through the absorber. So the gases travel in a circuit. Now we've got several kinds of circuits. We've got closed circuits, we've got semi-closed circuits, and we've got open circuits. What's a closed circuit? Closed circuit. Michael, you're going to tell us?
A completely closed circuit would be where the person's uptake of oxygen or their oxygen consumption would be equal to what you're putting into the circuit.
Right. Anything else? You just spoke of oxygen. Are there any other gases you might want to deliver?
Well, anesthetic would be nice.
Anesthetic would be nice. What about nitrous oxide? And what if you're taking up nitrous oxide? You'd have to add as much as the patient is taking up. So that's correct. Jennifer, what is a semi-closed system?
Basically what you're doing is you're putting in more than the patient's taking up, but you're putting in less than the total minute ventilation.
Right. And what would be an open system then? By elimination, it would be what?
No rebreathing.
Be no rebreathing. So those are the three systems. We could also talk about a low flow system. What would a low flow system be, Jennifer?
It's where the flow is equal to or less than half the minute ventilation.
Okay. What are the essential components of an anesthetic circuit, like the one we've got there? What are the essential components? Tell me one. Just tell me one. Any one.
Unidirectional valves.
Okay. Unidirectional valves. One-way valves. All right. You're on a roll. Tell me another one.
Of the circuit.
Just need to look at it.
Mm-hmm.
Name something.
The corrugated tubing.
Corrugated tubing. Name another thing.
The mask for the patient.
Mask or the connection to the patient,
Mhm.
maybe just the
Okay.
Y piece. Okay, what else?
And the rebreathing bag.
The rebreathing bag, right. Okay, she left anything out?
CO2.
CO2 absorber. See the absorber. And we also have to have the inflow and the outflow. Okay. Now, each of these has particular characteristics that we need to think about. Each of them is constructed in a particular way for particular reasons. And you should understand what those are. You also need to know, and none of you said this, but you also need to know that there are some non-essential components that people usually attribute to the circuit, like monitors or scavenging systems. Those aren't essential to the anesthetic circuit. Let's think about the reservoir bag. How big is it? How big is the reservoir bag?
3 liters.
Why 3 liters?
So you can have enough volume to provide a sufficient breath.
A sufficient breath meaning really
Tidal
almost a vital
volume.
capacity.
Right.
So the patient can take a deep breath or take a shallow breath. Well, why not make it 5 liters then? Or 10 liters? When I was a resident, they had 10-liter bags. What's the matter with a 10-liter bag as opposed to a 3-liter bag?
It's going to dilute the gases, probably.
It will
Or
dilute the gases, but functionally,
you-
there's a much bigger
You may
problem.
deliver too much volume with
You
it.
could deliver too much volume. You got a big hand?
Medium?
Medium. Okay. Let's suppose that rebreathing bag were 100 liters. Do you think you get your hand around it?
No.
You couldn't. And you couldn't really squeeze the bag, could you?
No.
So we make it a 3-liter bag rather than a 10-liter bag because
More
that-
control?
You got more control. Exactly. So, well, why not make it a 1-liter bag?
Because you're not going to be able to give enough volume with that.
That's right. The patient wanted to take a deep breath, couldn't take a deep breath. What about the compliance of that bag? Say it's at 1 liter. What's the compliance of that bag? Low or high?
High.
Very high. Very high. Is that what you want? Do you want it to be high?
Sure. Yes.
Okay. Why do you want it to be? That's right. Why do you want it to be high?
I guess so it can allow exhaled volume to come into it easily.
Easily, without any resistance. That's right. So you want over that entire range from 0 to 3 liters there to be a very low compliance. So if we were to draw the compliance, we might have something like this. So as the volume goes up, make this volume and this pressure here. As the volume goes up, the pressure scarcely changes at all until what?
So you fill the bag.
Until you fill the bag, until you get to 3 liters. And why at 3 liters do you want the compliance not to be high?
You want to be able to generate enough pressure in there to deliver a breath if you
Right.
need
And if the compliance were still very high, when you squeeze the bag,
it
you
would
couldn't.
deform.
It would deform, and the rest of the bag would pooch out, and you wouldn't get any gas into the patient. So you want the compliance curve to look like this. But you don't want this to go on forever, do you? Because then maybe you could exert too high a pressure. So the balloon, the reservoir bag, has been constructed so that it can expand forever without changing the pressure. Let's see that. So there's that bag getting bigger and bigger. And if we were looking at the pressure within the circuit, you'd find it would be at what pressure?
40 to 50.
About 40. About 40. It doesn't go above 40. So they have, unlike the reservoir bags that I had when I was a resident, this is a very cleverly made bag so that you can get bigger and bigger. It won't pop. You can get bigger and bigger without increasing the pressure. Let's look at the corrugated hoses. Corrugated hoses. They are built with a couple of specifications. One of them is the diameter. What's the diameter of the corrugated hoses?
22 millimeters.
About 22 millimeters of mercury. No, 22 millimeters, period. Okay, they're 22 millimeters. Why 22 millimeters?
I think it's a standard size to fit other adapters like onto your Y piece, your endotracheal tube.
Right. So they've standardized it to that, but why did they choose that as the standard? I mean, they could have chosen 44 or 88. Why did they choose 22? I mean, it's aesthetically a very nice number, 22, but why did they choose that? Why didn't they choose 5? It's a prime number.
Well, you'd have much higher resistance through a
You'd
smaller
have much
tube.
higher resistance. So they were considering resistance, and they wanted the resistance to be low. So they chose 22. Why didn't they make it 44? That'd be even lower.
Too cumbersome.
It gets too cumbersome, and it's more space to fill up. So you want to choose the minimum diameter that allows you essentially no resistance. And why did they make them corrugated?
So they won't kink.
So they won't kink. Let's see that. So there it is. Even though this has been doubled back on itself, these two tubes have been doubled back on themselves, they're still patent. It's difficult. You can do it. You can kink them if you really work at it. But it's difficult to kink corrugated tubing. So they've gone to all that trouble just to prevent kinking. Is that important? You bet. You bet. Kinking would completely obstruct breathing. And when we go back and look at this circuit, notice that there are 2 valves in it. Is that a belt and suspenders? We only need 1, but they give us 2 just to be sure that if one malfunctioned, the other one would be there. Is that right? No. I heard someone say no. James, you said no?
Yes.
You sure?
Yes, sir.
Okay. Well, now let's see. If we take this one out, this exhalation check valve, then when the patient inspires, oh, I see, they could draw gas back through there, couldn't they? Gas that they previously exhaled. And similarly, if we took this out, then exhalation could go down the inspired limb. There have to be 2 valves. Have to be 2 valves, one on the inspiratory side between the reservoir bag and the patient, and one on the expiratory side between the reservoir bag and the patient. And what about the character of those valves? Do you want them to be light or heavy?
Light.
Light. Why?
So that when on the inspiratory side, when the patient inspires, if you have a heavy valve, it takes more of an inspiratory effort to open that valve.
So you want to minimize respiratory efforts. Okay, that's fine. And what other characteristic do you want? Quinn?
Well, you want them to be non-sticky, to use a unscientific word, but they're made out of Teflon so that any moisture that comes on them will not stick to them and make them stick in the circuit.
Would you show us that?
Sure. Here we have the inspiratory and expiratory valves that were removed from the circuit of the Draeger anesthesia machine. These valves are made of Teflon and designed to be very lightweight. In addition, they're designed to be moisture resistant to prevent them sticking should moisture accumulate on them during the course of an anesthetic.
And then we have these 2 absorbers. Not 1, but 2. Used to be, when I was a child, we just had 1 absorber, and it was much smaller than this. They've gotten bigger, and they've put 2 on. What's the reasoning there? Why do you need 2 rather than 1?
So that you can completely use one absorber before having to replace it.
Right. If you want to, you can completely use 1 absorber before you need to replace it, because the other absorber will do everything that the first will do. That's all you need. All you really need is 1 of these absorbers. So you can completely use up the other absorber, and it's most economical. Why did they make them 1 liter? Why not half a liter? When I was a child, that's what they had. They were about a half a liter. That'd do. Why did they make them 1 liter? You got an answer over there?
It makes for a large enough volume so that there is a pause during the cycle, so there's efficient scrubbing of the CO2.
It just sits there for 1 complete cycle. And that's enough room. A liter is enough to accommodate almost all the tidal volumes that we have. Okay. What are they filled with, these absorbers? They're filled with absorbent. Well, and we decided that those were various bases and various combinations of bases. They're made up into little pellets. How big are the pellets? What's the standard size for the pellets? It's in meshes. What's the mesh?
4 to 8 mesh.
4 to 8 mesh. What does that mean?
Well, it's how many granules you have per unit of volume.
Okay. It's done with screens that are 4 to 8 meshes per square inch. And why did they pick that?
Well, if it was a lower mesh, in other words, you had finer particles, it would be too much resistance to gas flow through it. And if it were larger particles, then there would not be as efficient scrubbing of the CO2.
So this is the optimum size for absorption and minimal resistance, and that's correct. Now, we've previously considered how the alveolar concentration of an anesthetic would change if we delivered a constant concentration from the vaporizer or a constant inspired concentration. The reality is that when we're maintaining anesthesia, we vary what we deliver in order to keep the alveolar concentration constant. And let's look at some implications of this. First, for a closed circuit. For a closed circuit, we have to know how much anesthetic is being taken up. What are the absolute amounts of anesthetic taken up at a constant concentration, say 1 mEq. And this graph indicates that uptake for the first hour of anesthesia. The uptake of desflurane is more than the uptake of sevoflurane. Why is that? Because what?
I was thinking less potent, but I'm rethinking that answer.
That's correct. No, that's the right answer. That's the right answer. 1 mEq of desflurane is what?
6%.
6%.
Yeah.
And 1 mEq of sevoflurane is?
2.
2%. So you got to deliver more desflurane to compensate for its lower potency. There's a 3-fold difference in potency. However, the curves are roughly a little more than 2-fold different. Why are they only 2-fold different? Because of? Right. Okay. And in fact, with isoflurane, there's a 5-fold difference in potency, but only less than a 2-fold difference here because of the difference in solubility. Which is the more soluble agent? Isoflurane is more soluble agent, so we need more to replace more anesthetic that's taken up. Now we can consider what vaporizer setting would be needed in order just to deliver this amount of anesthetic in a closed circuit, that is at about a 200 mil per minute of oxygen going through the vaporizer, say a variable bypass vaporizer. And when we do, we find that at 1 mEq you can't deliver enough anesthetic. This is now the delivered concentration relative to the alveolar concentration. So for sevoflurane, the alveolar concentration would be 3%. For desflurane, it would be 6%. I'm sorry, for sevoflurane it would be 2%, and for desflurane it would be 6%. For isoflurane it would be 1.15%. The desflurane vaporizer maximum setting is what percent? 18%. So you could deliver 3 times what you wanted to obtain in the alveoli, but it wouldn't be until you got to about 10 minutes that you could deliver enough to replace the amount that's taken up. Sevoflurane, what's the maximum setting? 8%. 8%, but it's going to be out here at about 14 minutes before you can deliver that with a sevoflurane vaporizer. And with isoflurane, you can never deliver it in the course of the first hour. Now that presumes you were giving 1 mEq, but if you were giving nitrous oxide, you wouldn't have to give 1 mEq. Maybe you'd only have to give half a mEq. If you have to give half a mEq, then you probably would be able to deliver the needed concentration in the first minute or so of anesthesia with either desflurane or sevoflurane. Still might have a little problem with isoflurane. Now things change with a semi-closed circuit. If you're delivering a 1 liter per minute inflow, here's the delivered concentration relative to the alveolar concentration. The alveolar concentration is fixed, so this is how much higher the delivered concentration has to be. With desflurane, it's got to start out at somewhere around 2.7 times as much as is in the alveoli to make up for the uptake. It rapidly decreases. Why is that rapidly decreasing for both desflurane and sevoflurane? And for isoflurane if we extended the graphs? Why is it rapidly decreasing in the first 4 to 8 minutes?
Saturation of the vessel-rich group.
Saturation of the vessel-rich group. Give that man a cookie. That's right. Say that again.
Saturation of the vessel-rich group.
Saturation of the vessel-rich group. Okay, so we've got equilibration that is completed in the first 8 minutes or so, maybe 10 minutes or so. And after that, we've got it decreasing further as what happens?
Muscle group saturated.
The muscle group is being saturated, gradually equilibrated. So we get out here at 60 minutes, we see that the dial concentration needs only be about 20% greater than what's in the alveoli with desflurane, maybe up here at about 35% with sevoflurane. But way up here with isoflurane, it has to be twice as great as what's in the alveoli. You've got much better control with those poorly soluble anesthetics, with desflurane and with sevoflurane, than you do with isoflurane. And the vaporizer setting, the FD, is not too far from what you're trying to achieve in the alveoli. And it gets, of course, even closer as your flow rate goes up because of what? What do you do when you increase the flow rate? You decrease
Rebreathing.
You decrease rebreathing. So it gets even closer. We've expanded the y-axis here. So now this goes from 1 to 1.8. And you can see that at a 2 liter per minute inflow rate, it's only a little more than 10% greater for the desflurane than what's in the alveoli, and maybe 15% or 20% for sevoflurane. Now finally, I'd like to return for a moment to the issue of cost, and just remind you again how important flow rate is to the issue of cost. The anesthetics that we have, the inhaled anesthetics that we have, can either be expensive to use or cheap to use, and you are the people who are going to determine whether they're expensive or cheap to use. It isn't just that sevoflurane and desflurane are more expensive anesthetics, because they're not generic. They're still patented. But because we can use them at different flow rates. So if we use desflurane and sevoflurane at a 4 liter per minute flow rate, we're talking about anesthetics that are going to cost us at MAC, when we want to keep it at MAC, going to cost us $25 to $30 an hour. And that can be a very expensive proposition if we're talking about anesthesias that are 2, 4, 6 hours long. On the other hand, if we get down here to 1 liter per minute or less, we're talking about anesthetics that cost us $10 per hour or less. And when we add in the factor of nitrous oxide, which may decrease our requirement by roughly half, all those numbers go down by approximately half. The one limitation to cost saving by a decrease in flow, of course, is the limitation that applies to sevoflurane, that we should at least keep it at 1 liter per minute or greater.